Hello, everyone. So we will start. So I'm Gilles Saint-Martin. You have my contact information on the bottom here. So I'm an entomologist living in Belgium. I'm working in an agricultural research center, and I'm also a data scientist. And I've been looking at various data sets for the last almost 20 years now. So I've seen a lot of different data sets, analyzing a lot of data for different people. So I've seen a lot of various problems. So that's why I give you some feedback based on my experience, but also on the common experience of the data science community. Basically, everybody is experiencing the same kind of problems. So we will have three main parts in this presentation. First one about, well, introduction, context, a few definitions just to know what we are talking about, and basic principles. And then the two main parts will be, the first one will be about which data and metadata should you almost always systematically collect. And the last one is, once you know what to collect, how to organize your data in a way that will make the data analysis easier afterwards. Before starting, just a few articles and literature that I think are really interesting about that topic. And particularly if you are not a researcher yourself, I will really recommend you to read, for example, these two first paper. They are really not too technical, and they are really a good summary of what we are going to discuss today. And if you are a scientist yourself, I also highly recommend you to read the last one here, which is really wider than what we are going to discuss today. It's also about reproducible research, open format, open data, collaboration, etc., etc. So it's really a good paper, I think. And finally, there is also good resources about the topic we are not going to discuss in detail today because we lack the time. It's really about how to organize your files and your data folders. And there are several papers discussing that and giving you a different example of how to organize that. So first part, introduction. Basically, the context is that in science is more and more collaborative, computational, and data-driven. So collaborative means that you probably more and more people are collecting data, but they are not necessarily the ones who will make the data analysis. So probably if you want also advanced data analysis, you will share your data with other people who will make the analysis. And also science should be as much as possible reproducible, and to do that, I think one microphone is still open. So to do that, scientific results to be reproducible, one of the basic conditions for that is that everybody should be allowed to look in details at the data set and try to reproduce the result, for example, for a paper. So to do that, you need to share the data with the paper. So this means that even if you collect the data for yourself, it might in the end be used or viewed by other people. So the general rule, which is a kind of very big summary of everything we are going to discuss afterward, is that even if you collect data for yourself, you should collect it and organize it and describe it in such a way that somebody else than you could go in your data folders and understand what is in the data, and could use it even for different purposes that what you intended the data to be used for. And also, and that's very important, without any additional input from you. So everything should be in the data, everything should be described, so that anybody can just take your data folder and understand the content. And so to do that, you must do something that is sometimes a bit difficult. You should put yourself in the shoes of somebody who don't know how you collected the data, who did not participated to the data collection, etc. And an important fact about that also is that the most frequent beneficiary of this procedure is your future self. Probably everybody here has already experienced the fact that you collected data something like 3 months ago or 3 years ago. And when you go back to your data, you don't exactly remember how you collected some data, where are the data, etc. So if you take if you systematically organize your data for other people, it will be also better for your future self. Another general rules is to ensure data quality, integrity, availability, traceability. I will not spend too much time about that because it's too general and generally it's too abstract and it is not very informative. But from these very general rules, you can derive very simple and practical rules. And this is the topic of this workshop. We are going to see a lot of very practical examples that are derivatives from these general rules. And so the question could be also, why is it important? And basically, if you don't follow this rule, you have three major consequences. The first one is, of course, poor data quality. So you will have errors in your original raw data, but also in the process of the data manipulation and data analysis, you could add new errors, and errors will accumulate over time. Another big problem is loss of time. Most data scientists will tell you that the majority of their time is dedicated just to mundane tasks like tidying the data, cleaning the data, and it will be really better to devote this time to other more interesting tasks like new data collection, analysis, and communication. And finally, there is this question about reproducibility. The final result might be impossible to reproduce from scratch if you don't follow these rules, and reproducibility is key in science. But this is not the main topic of this workshop. In fact, having a clean data set and clear data sets is just the first step to have reproducibility, and you need more stuff, and we are not going to discuss that today. Okay, another question is, why is it so frequent to have messy data? So if most data scientists spend most of their time just cleaning the data, it means that generally the data is not in very good shape to begin with. One reason for that is maybe a lack of data literacy. And the idea is that many people who collect the data will never analyze it, or will make very simple data analysis, like in Excel, make a few graphs or calculate a few averages. So this is not very advanced. And so if that's the profile of the people who collect the data, maybe they don't understand exactly the consequence of some choices. Another frequent problem, I think, is that we have a strong tendency, and including data scientists, to shape the data, to organize the data so that it looks nice for humans. But the problem is that for the data analysis step, you always need computers, and computers don't see the world as we do, as we humans do. And so basically you have to put yourself in the shoes of other humans, but also of the computer, and understand how the computer needs to have the data so that it could be analyzed precisely. I will come back a lot to this distinction between humans and computer during the session. And finally, there is a kind of heavy debate about spreadsheets. So spreadsheets are really widely used. And the problem is that intrinsically, they do not protect you against frequent problems like other systems like relational database would do. And even sometimes it will encourage bad behaviors. And even sometimes the spreadsheet will itself create errors and change the data without your consent. So basically, the use of spreadsheets is sometimes a bit problematic. So if you can avoid using them, basically you should. But the problem is that often it's too time consuming to build a huge database for a simple project, for example. And basically spreadsheets are so flexible and so easy to use that, well, many people will continue to use it. And personally, I still use it too. So the question is it possible to do a good job, nevertheless, if you're using a spreadsheet? And well, some people will answer no, it's not possible. But well, probably a more reasonable answer is that yes, to some extent it's possible, with two conditions. First, you should have a project that is not too big, with not too much data and too much people involved. And the second one is that you must be aware of some pitfalls involved with the use of a spreadsheet. And basically, this is the topic of this workshop. Is really targeting people who are using a lot of spreadsheet to encode the data and maybe manipulate the data. So now a few definition. We will not spend a lot of time defining terms. It's always complicated to define terms, but it's just to agree about what we are talking about when we say data, when we say metadata, etc. So data is a very vague term. Basically, it means any item that could be analyzed to extract information or insights. And typically, historically, it has been always text on numbers. But it could also be something like images and sounds. And computers are becoming better and better to understand what is in images and sound. But in this workshop, we are mainly concentrated ourselves on the text and number data. We can also make a distinction between unstructured data and structured data. So unstructured data is any data without predefined organization. And generally, this is better suited for humans as soon as you don't have too much data, and less well suited for computers. So a typical example is a free text written by a human. It will be complicated to analyze that with a computer. And structured data on the other side is data organized in a systematic way, and generally computers prefer this kind of data, but it's less user-friendly for humans. I will give you straight away some examples. So you have an imaginary example here of unstructured data. Basically, it's a question about what are your practices to control varromites in beehives, and you have 3 imaginary answers from 3 different beekeepers. And you can transform that in structured data in a tabular format. What you can see is that when you do that, generally you lose some information. So for example, here, the beekeeper provide the exact date, so the 2nd of August, and you can see that here we didn't kept this information about the day, we only kept the month. The varroa treatment, it's also a little bit less precise. But even more than that, if you read the answer here, a human can have an understanding somehow of the psychology of the different beekeepers. So the first one is very precise, the second one not precise at all, the third one is precise but a bit secretive. You don't want to share this information. This is really something very fine-grained that only humans can grab. Not only it's possible to analyze the feelings, but it's really more dedicated to sociologists or psychologists. But in environmental sciences, generally we need some kind of structure to analyze the data, and so it's always better to think about how to make this data in a structured form like this. And this is structured, the tabular format, but it is still relatively human friendly. A human can quite easily understand what is in this table. Here under, you have another example of structured data, but it's not a tabular structured data, it's an XML format. It's dedicated also to bee data. And you can see that it's extremely structured, but for humans, it's already a bit more complicated to understand the exact structure. So again, in this workshop, we are not going to speak about this kind of structured data. We are really concentrating ourselves on the tabular data. Then you have metadata. It's also quite vague. The definition is basically data about data. It's information about data to help humans to interpret what is in the data. You can also have unstructured metadata. It's just a text describing, for example, the methodology, the context. That's the most frequent one. But sometimes you can also have a structured metadata. So for example, a code book, a table describing each column of each table. And we will see a few other examples. And the limit between metadata and data is not always very clear. So in this workshop, the limit I will draw is I will consider that metadata is information about the data which is valid for almost all samples or all sampling units. And typically this information is stored outside the data table in separated files, and generally they have a conventional name. A typical name is readme.txt with uppercase readme or codebook. These are the two most common names for metadata information. On the other hand, data is any piece of information that will be different for each sample, or each record, each observation. So for example, the date could be both metadata or data. For example, if you do a lab experiment and it was done on one specific day, it will be valid for the whole data set. So it will be more in the metadata. You describe that in the metadata when the experiment took place. But if you collect samples on the field in different apiaries, in that case, each observation, if sample, will probably have slightly different dates, and it will be stored in the data and will be considered as data. But the distinction is not that important. What is important is to collect the information and to store it in a way that is understandable for other people. I will now provide a few examples of unstructured and structured metadata so that you can see typically what we put as information in this kind of file. So here's an example of unstructured metadata. It's a text file simply describing the context and the basic methodology related to a project, to a data set. And it's pure text. It's just that maybe you can see strange formatting here is because it's written in Markdown, which is a kind of raw text that can easily be transformed to HTML or doc or PDF. So this means, for example, this is a title of level 2. It's quite common in the data science community. So it's just plain text, readable for human and not really usable for computers. Here is another example. In that case, what we do is for each data file from the project, we will provide a short description, of the content of the data table, and also a short description of the content of each column. So each bullet point here corresponds to one column, including the units, for example, the measurement unit, and a few additional information. We have an example for one table here and another table here. So that's quite common. But you can have the same kind of information in a structured format. So this is an example of what we call a code book. This is the Colos code book for honeybee winter mortality survey. And basically, you can see that you have a column with the name of the column from the table. So you have the data table, and this is the name of each column of the data table. You have a short description about what this is about. You have the question number because this is a survey, and then you have coding instruction telling you that, okay, for this question, 1 means better, 2 means no differently, 3 means worse, etc., etc. So a question is, when should you use structured metadata and when should you use unstructured metadata? There is no strict rules. But I would say that probably if you have a lot of columns and a lot of tables, probably a code book with a structured format like this one is probably better. And there is another situation is when the metadata, so the names, for example, here, should be manipulated somehow by other people. In that case, it's much better to have that in a structured tabular format. I will give you an example about that just with this example of Colos codebook. So this is a European project. So the coordinators send us this codebook telling us this is what we need as data, and you should organize it like that. But in Belgium, we have our own survey, online survey, and in our online survey that is performed with Lime Survey, a software called Lime Survey. This is the name of the question in our Lime Survey. So we use that to make the correspondence between our name in our survey and the name expected by Colos. And also we have a series of questions that we ask at the Belgian level that is not asked by Colos. This is typically, for example, the personal information of the beekeepers, their name, their address, emails, etc. So this is information that should not be disclosed. So this should be very precisely identified. And also other questions that we ask in Belgium, like the race, for example, that the beekeepers have used. And we also have for each question, the local language question. So the question in French, in Dutch, and in German, because in Belgium we have 3 languages. So it will be much more difficult to do that if the Colos codebook was not in a structured format like that. So in that case, it's a very good thing that it's provided in a structured format. This is another case. It's a case where in this project, you can see that you have a lot of tables. So it's really a lot. And if somebody else than you should understand what is in this table, it will be quite difficult because of the number of tables. So sometimes the raw data, the metadata, sorry, you can first begin with some kind of guidelines to find your way about which table are the most important. So you can see here that we explain, okay, we in this project, we make 5 groups of measurements about pesticide, pathogens, pheromones, pollen identification, and antioxidants. And we cite the most important tables related to each of these topics. So we don't provide information about all the table at this point. It's just a way to organize yes, which one are the most important. And afterwards, so in the second time, you have the details for each table and each column in each table with all the description. So it's really for more complex project. And again, it is this idea, you should put yourself in the shoes of somebody who don't know your project. You should help them to understand what is in the files. Okay, now just before I begin, a few basic principles of data quality management system. So quality management systems, if you are in the industry, you have heard about that a lot. If you're in the academia, maybe less. At least when I was in the academia, I never heard about data quality management system. I didn't know what it was. It can be really complicated and sometimes a bit boring, but there are key concepts that are still very interesting for anyone, I think. So I extracted a few of them that I think are really important. So basically, such a system is always a never evolving and improving system over time. So the idea here is that no one is perfect. You always make errors, and you can always improve yourself and improve your system and the way you collect the data. And they also stress a lot the importance of training and communication. So if you see that you have some difficulties in one domain, you should train yourself to be better at this part. And then the quality management system should ensure the data integrity, the data traceability, and the data quality. So by data integrity, we mean you should find a way to avoid data loss, data destruction, accidental modification, etc. I will come back to that just after. Then you have data traceability. The idea is that when you have finished your statistical analysis, for example, you have an average value, you should be able to know, okay, this average value, with which data it has been computed, how it has been computed, and from where this data come from. You should know, for example, who collected this data, with which kind of material, at which date, etc. So you should be able to go back to the raw data from the final data. And then you have the data quality. So the data should reflect your observations. And you know that you will always have errors. So you have to keep in mind that humans always make errors. And personally, I always consider that in each data set, I will always have errors. I think I've almost never seen any data set without problems, without errors. So what you should do is evaluate the probability for errors to occur, and then evaluate the potential impact for such error, because sometimes there are errors that are not so impactful, so maybe it's not that important, but you should really anticipate the most problematic one. And then you can do two things. First, you can take action upstreams. So before collecting the data, in order to prevent this error to appear, there are very simple actions that can help to do that. We will see that afterwards. And the other one is, once the data is collected, you know that maybe there will be errors in them. So you should have some data quality check afterwards, after the data is collected, in order to spot these potential errors and take action with them. So the core of the rest of the workshop will be about this part. But first, I will just speak a little bit more in detail about data integrity. So the first data integrity rule is backups, 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 backups. You really need to make backups of your files in physically separated location. And this is really important because fires can happen, flooding, theft, loss, etc. You really should not think that this happened only to other people. I have personally experienced fire, theft, and loss, and I have lost data because of that. So if your backup is at the same place as your computer and your house burns, then you lose everything. So it should be really in separated places. Sometimes we have a paper form. So personally, I still have a real paper form like this one. So a good practice will be to scan the paper form and keep them with the raw data files. So this will be a backup of your paper format because again, the paper can be lost, can be burned, etc. And also it's interesting because it's then easily available for data checking. So typically when you analyze the data, if some of the data looks strange, you think it's bizarre, you can go back in the raw data. So for example, the paper form to check if it's not just an encoding error, for example. Another option that is available today is storage in the clouds. So for example, on Google Drive or something like that, it's very quick and easy for small files. So it's a way to have a backup in a physically separated place because the server is somewhere else than your computer. And we also have now online spreadsheet tools like Google Sheet, for example. And generally, this kind of tool includes a very interesting feature, which is an historic of the changes. So that might be really interesting, for example, to restore a previous version. If there has been an error, an accidental modification of the data. So for example, in Google Sheet, you can just right-click on a cell, select Show Edit History, and then you can see who modified this data and when. And you can go back in time like that. You will just lose that information if you make a copy of the file. So it's only on the original file, but it can be really interesting. So backups. And the second rule that is really important and maybe even more difficult to explain and to enforce is to keep the raw data raw. So the idea is that you should never do any manipulation in your raw data files. The raw data files is only for data encoding, so you can add new data, but you must absolutely never do sorting of the columns, copy pasting, making graphs, calculating averages, sums in your raw data. If you want to do that, you should make a copy of the file, and then you can do what you want in the copy of the file. The reason for that is that in spreadsheet in particular, it's too easy to modify or even completely destroy your raw data if you do that. It's extremely easy to do that. So you have this funny Twitter account here. So well, if it asks, do you want to save the changes made to the document raw data that should never change? The answer is don't save. You should never. You should even don't have that kind of messages because you should work on a copy of the file. So how you could destroy your data set. This is one of the most common example of how you could destroy your raw data. Is simply by sorting the file. So this is an artificial example here, of course. It will be obvious here, but when you have a huge data file, sometimes you do that and you don't realize that you have done that. So the idea here is that you have this, you click simply on the button to sort the data. And what it will do, it will only sort this part of the data because you have an empty column here. So you can see that the sample identification here is still the same between the two print screens, but the value have changed. So basically, when you do that, what you do is randomize your data set. So the height and the weight are still together, but they are not corresponding to the right sample ID. This is in LibreOffice. It does that without any warning. So you just click and it will randomize your data. So if you realize that immediately, you can undo. But if you don't realize that immediately, your data is lost. So that's why it's really important to work on a different data set. By the way, in Google Sheet, it seems impossible to have that problem. So it depends on the software. In Microsoft Excel, this is a common problem that is known for a long time, but it seems that it will provide a kind of warning like that. But you know that the warnings often you don't read them and you click sort and then it's too late. Another very common example is that you want to reorganize your data and you're going to do a lot of copy paste and a lot of manipulation in the data. copy pasting to rearrange the data is highly error prone. I know that sometimes you cannot avoid it, but you have to know that you will probably, it's highly probable that you will make errors by doing that. A typical and really serious problem you can have is a shift by one line of a part of your data set. So it's again an artificial data set. It's small, so it is easy to spot here. But in a large data set, it's sometimes quite difficult. And in fact, I have seen that several times in real life examples. So the idea here is that you make a lot of copy paste, and at one point you end up with this data set. And you can see that, for example, the S009 sample, the real value is 18, and you can see here that it has changed simply because everything has been shifted by one case, by one row up. So nevertheless, you almost always need to reorganize your data before data analysis. So what you should do if you have to do that. So the key idea is that you should keep a separate directory with your raw data and never touch that raw data unless you need to encode new data. You should create a clean data in a separate file and probably in a separate directory. And then you can do your copy paste it if you need it, but you should have somewhere a trace about how you have you pass from the raw data to the clean data. So how you pass from the point 1 to point 2. There are two main ways to do that. Ideally, you should do that with a computer script, so with a programming languages like R or Python or something like that. By doing that, you don't do any copy paste, and every step is explicit because it's just command line to the computer. But of course, I know that not everybody is willing to invest in learning a whole computer language, and many of you will probably nevertheless have to do copy paste. That's not a problem as soon as you understand that this is dangerous. So that's okay. So in that case, you use copy paste, and you should describe with words what you have done, how you pass from the raw data to the clean data. And then in a fourth step, whatever, even if you use a computer script, because you can still make errors with a computer script, what you should do is downstream quality check. So after you have made all your modification, check if you don't have errors. And how to do that? There are many ways to do that, but one way is to compare the raw data with the clean data. That's why it's important to keep them separated. So you will you will select at random, I don't know, few lines in your data set and compare if the raw data is still in line with the new data. So for example, here, what you will do is compare this line from the raw data with this line with the clean data, and you will realize that there has been a problem. If you did copy paste, probably you should redo everything. If you made a script, probably you should just modify the script and rerun the script. There are many other ways. You can also, for example, count the number of data record you had at the beginning and the number you have at the end. And if you didn't remove anything, you should have the same values. You can also compute, for example, an average value. So for example, here you could compute the average value of the height and see if it's still the same here. It's not perfect. So in that case, the average would probably be the same in the two. But if it's different, you have a clue that maybe something went wrong. So there are many different ways to do that, but you should do that. And then in the fifth step, you can perform the data analysis, but only on the clean data. And again, never touch the raw data. You have a lot of discussion in this paper about that topic. So this is an example of a real data set where you see the structure of the data. You have a folder with the clean data, you have a folder with the raw data, and here you have an R script simply that transform the raw data into the clean data. So you have all the steps to pass from the raw data to the clean data. Okay, so this is part 2. So now that we have the generality, the question is, okay, which kind of data should I almost systematically collect? And you might think that, okay, I'm the scientist, I know what kind of data I need, but in fact, I've seen many data sets where some kind of information was lacking, and it was really annoying for the data analysis. Basically, the idea here is that you should collect and provide, because sometimes the data is collected, but it's not available. So it's a problem. So you should collect and provide data or metadata to answer the following question: why the data has been collected, who collected the data, how the data has been collected, when, where, and what is each data record about. I will go in detail for all of them. And maybe the first one are the less critical or the less complex, and the last one are the most difficult. So why the data was collected is simply provide the context and the scientific question that you wanted to answer when you collected the data. So this is basically the introduction of the scientific paper, but much shorter and much straight to the point. It should be really short, just explain the context basically. And typically this is unstructured metadata. It's just a text providing this information. This is another example here. Just by reading the title of the dataset, you know the context and what is in it. It's occurrence data, it's bees, it's in North Tanzania, and it's agricultural and grazing gradient. So you have almost the gist of it in the title. The second question is who collected the data? This could be in the metadata. So for example, here you have the authors of the data set. So that's just a general information that is valid for the whole data set. But sometimes also you want that in the data. You would like to know which operator collected which data. And why would you like to have that level of detailed information? It could be for the data analysis. So for example, you want to test if there were differences between the operators. But most often, in fact, if you have a good statistical design, normally you should have randomized the sample, the measurement between the operators. And so even if you have differences between the operators, this should not be a huge problem for your data. So that's why I think this is not so often used in the data analysis. So this is more important for the traceability of the data. So for example, again, you realize that something is strange in your data. You want to go back to the operator who did the measurement to ask question, why do we have this strange value? Sometimes also, and I have experienced that, you realize afterwards that one of the operators didn't understood correctly how to make the measurement. So in that case, it's really useful to be able to extract the measurement made by this operator and choose what to do. In my case, we simply removed all the measurement made by this operator. And in that situation, it's generally a problem of communication and training. So it was my fault. I was not clear enough with this operator about how to collect the data. This is a very simple example of a data set for each sampling, for each measurement. You have the information of the operator here, who did the observation, and also the research team, because you had 3 research groups who did the observation. This is another example where this is information that is not really in the data. This is a form that is close to a scale. And the idea is that we want to know who used that scale and when. So this is not really useful for the data analysis. Again, it's more for traceability. If at one point you realize that there has been a problem with the scale, you want to go back to the people and tell them, okay, there has been a problem, and they are informed and they can take action about their data sets about that problem. So the third question, how the data was collected. So basically, this is the methodology. This is generally not a problem. Often the methodology is provided. So most of the time it's just a material and method section of a paper, and it's provided as unstructured text in the metadata. But there is typically a kind of data that is often lacking. And sometimes you need data about metadata about the methodology in a structured format. And the example I have in mind here is when you have pesticide multi-residue analysis, so you analyzed the content of pesticide in for example, in pollen. What you need is the full list of pesticides that have been looked for in the project, not only the result for the detection, the pesticide that have been detected, but also the one that have never been detected. And you need a limit of detection and limit of quantification for each pesticide and each matrix. And you need that because it's crucial to interpret the data, and particularly the absence of detection. The absence of pesticide will depend on the limit of detection. And it's also crucial when you want to compare different projects, different results for different studies. This is typically a kind of data with which metadata with which we have problems. Either it's not available or not in the right format. It's often problematic. So this is an example of metadata table with the LOQ, LOD for each pesticide and each bee matrix. You can see that often the LOD is not the same depending on the matrix, so you have to have this detailed information. And this is an example of what you could do with this kind of data. So this is a graphical representation of the quantity of pesticide found in 2 different projects. So each point is a sample, is a value from a sample, but we represent the LOD of the 2 different projects on the graph. So this is really what you need to do, because it's too complex information to just look at a table like that and really understand what is going on. With that, you can really have a better understanding on the data. And for example, understand that, okay, you didn't detect anything for this pesticide here, but the limit of detection for this one was much higher than for the other ones. So to do that, in order to do that, you understand that you need that in a structured numeric format. And you don't always have that. So this is a real life example from a project. First, they didn't provide any information about the LOQ and LOD. When I asked, they provide that, and they had only that information. And it's a bit blurry. It's because it was a scan from a PDF of a report. And so what's the problem with that? You might think, okay, we have the information we need. And indeed, for humans, this looks like a table. But again, for a computer, this is just an image. And if you want, for example, to compute the average of the LOQ, it's not possible with that. So the only way to use that information is to re-encode everything by hand. There is no other way, because even with OCR, the quality of the scan was too bad, and it will not really be possible to retrieve that information. So the idea here is that for this kind of data, it should be provided in a structured format and not as a table in a PDF, for example. But I understand that, for example, if you are a lab and providing this service to clients, some clients will expect and will demand a table like that in a PDF report. Probably, I think in that case, the best behavior is to provide both information. So one, a nice looking table for humans in a PDF, but also a structured data table in CSV file or an XLS files or something like that. This is another way to organize LOD and LOQ data. I will not spend too much time on that, but you can read the presentation afterwards if you are interested by that. So another question that should be ideally answered is, when was the data collected? Again, this is particularly interesting for a field sample or field observation, and this should then be in the structured data, but it could also be useful for lab measurement. So for example, to know, okay, when did you use the scale, when did you do the experiment? Again, it's a question of traceability. If there was a problem in the lab, you should know when it took place, when the experiment took place, to see if it's a problem. So if it's in the data, a few recommendations. First, generally, we prefer the date in this format. So the year, a dash, the month, a dash, and the day, and the month and the day with 0 if it's below 10. This is an ISO formatting, and it has a lot of advantages. The size will not change, it will be easy to sort, and also it's less ambiguous. A common way to encode dates in spreadsheets is like that, so 2/3/2016. The problem is that depending on your country, this will not be interpreted in the same way. So in some countries, this will be seen as the 2nd of March, and in other countries as the 3rd of February. Normally, this is not, there is no ambiguity if your structure is like that. Another point is that sometimes you don't need one date, but 2 dates. A typical example is traps. So if you put, for example, pollen traps on a beehives or insect traps on the field, typically you need to know when you set up the trap on the field, and then when you collected the sample, to know the duration of time during which the trap was active. And so that's very easy. You just have two columns, one with the starting date and one with the ending date. There are two typical problems in spreadsheet, in particular with date. The first one is consistency. So the fact that the operator will not respect your format, the format you asked, they will encode the date in different format. And there is another huge and really complicated problem, which is autocorrection. Basically, spreadsheets, and particularly Excel, tend to automatically detect dates even when it's not date. So for example, in text column, and change the value without even asking. And this has been recognized for at least 10 years as a huge problem in genomics, because for example, in some gene names, you have, for example, sept4 for septin4 and march1 for membrane associated ring CH type finger 1. And Excel will recognize that as a date and automatically change that, for example, to 4 September and 1 March. So it will change your data. Another typical problem is it will think that this is a scientific notation, and it will transform this text into a number, a scientific number like that. It's sometimes very difficult to avoid that. So it's really a pain in the neck. It's one of the big problems with spreadsheet. So here you have an example. I have a sample ID, and the sample ID is 24/6, and you can see that here it's Google Sheet. It recognizes that as a date. So if possible, you should avoid using slashes and any other special character. The only acceptable one is the underscore, but sometimes it's not possible, because if it's the rule in your lab, you should use it. So you should be aware of that. And the only defense you can use, for example, in Google Sheet, is to format it as plain text. In Google Sheet, it works quite well, but I know that for example, in Excel, sometimes even when you do that, it's not enough. You should also be aware that, for example, here, if you ask for this value to be a number, it will completely change the value. It will provide this number, which is the number of days since the 1st December 1900s. So it would really change the value. And another danger is that it could change this value into, for example, 14 June or 6/24 or something like that. So it's really a problem you should be aware of. Then you would like to collect date and to force the operators to use the format we discussed before. So the year, then the month, and the day. The problem is that, for example, here in Google Sheet, even if you ask a custom date format and you choose that format, it will still allow the user to encode everything they want, and they will not transform the date encoded like that into the right format. So for the moment, maybe it's possible, but we never found how. So the only way we find in Google Sheet to enforce using the right date format is to choose not date, but a plain text format, and then use a data validation rule using a regular expression. So regular expression is a way to describe a string. So here it's just say, okay, it starts here, then we expect to have 4 numbers, then a dash, then 2 numbers, then a dash, then 2 numbers again, and then the end of the string. So it's crazy that it's so complicated to do something simple like that, but it's like that. And by the way, this is a good, generally using this data validation rule is really a good practice in spreadsheets. So to enforce the user to really encode only the data and the kind of data that is possible for each column. So here, for example, you can see here that we checked this box here. So we ask it to reject the input if the data is invalid. So no, if you encode the date, sorry, if you encode, sorry, if you encode the date like that, it will not allow you it will not keep the data, and you will have a pop-up windows that tell you that it's not the right format. You can see also here that this is a valid date and the format is correct, but this is probably an encoding error. The year is not correct. So probably you should put a little bit more effort to just constrain the date a little bit more. And for example, for regular expression, it's possible here. Okay, another question is, so we went on when the data was collected, and now we are on where the data was collected. Again, it's particularly important when you have field samples collected in different locations. The key idea here is that you should be as precise as possible with the location. Ideally, you should have geographic coordinates, but if you are not collecting the data yourself, for example, for an online survey, it's not always easy to have that level of precision. So you can ask the location in different ways. So for example, you can have a locality name. The problem is that often you have inconsistencies, typos, etc. So if possible, you should have a predefined list of localities, but it's not always possible. Another way is to ask a zip code. This is a popular way to have a location, particularly for online survey. I think the reason is that most people will know the zip code, the postal code, and they are easier to check for validity. For example, in Belgium, all our zip codes are a number between 1,000 and 9,999. So it's easy to check that the zip code is correct. The drawback is that the exact delineation of zip code is generally not publicly available, at least in Belgium. It's not public information, so it's not always easy to know exactly where it is. But what you can have is an approximate coordinate. So geographic coordinates is really the best. But if you collect geographic coordinate, I think you should also collect at least either the locality name or the zip code. And the reason for that is that you often have errors in the geographic coordinates. So it's a good way to check to check for errors in the geographic coordinates, to check with other source of information about the location. And also a remark is that even if for your project it's not useful to have the exact location, I think you should collect it anyway. The reason for that is that today you can have access to a lot of spatial information. For example, meteorological information, the information about land use, about the soil, etc. So it can be really useful to have the exact location of your sample to collect this additional data, maybe to answer other questions than the ones you're interested in. So a few geographic coordinates is often problematic. We often have problem with them. So here it's quickly a few recommendations about that. So the first recommendation will be to use decimal longitude latitude. So it's, for example, 15.2635, and to avoid degree, minutes, and second notation, DMS. So like 50 degrees, 26 minutes, and 3 seconds. The reason for that is first that this is not a number, it's a number and text, and it's basically to make transformation, it's almost better to have a number, and at one point you will probably need to transform that into a number. And the problem with that is that it's very error prone. So if humans are encoding this information, you will often have problems because the structure will not be exactly the same. You will have spaces, etc. So it's always problematic. So I think it's really much better to have the decimal degrees like that. Another point is to use longitude, latitude, and to avoid transformed, for example, projected coordinate systems. So for example, in Belgium, we have 5 different Belgian Lambert projections. So it's sometimes difficult when people provide projected data to know which one has been used. So if you use something exotic like that, you should at least provide a code. There is a EPSG code, which is a unique description of the geographic system coordinates. And also another point is that if you collect data from different sources, and that in these different sources, the type of coordinates system is different. So for example, you have longitude, latitude, and Lambert projected data. You should keep that information in the data. This is the original geographic coordinate, and then you can make a transformation of that to uniformize that. The problem here is that it's quite frequent that in this transformation you have errors. So it's really important to keep the raw data, to go back to it if you realize afterwards that you have errors. And in some database, it is not the case. You only have access to the transformed data with the errors, and you don't have access to the raw data anymore, and that's a problem. Another point is that these coordinates must be as precise as possible. So you should have at least 4 decimals. A common problem is that the geographic coordinates have been rounded, for example, to do 2 decimals. This is not precise enough. And another frequent problem is that people collect the coordinates with a car GPS. And so you will have the information, but the location will be on roads. And so if you want to collect, for example, the information about the crops that were cultivated during the last 5 years in the field in which the sample has been collected, because the point is on the road, it will not be accurate enough. So it's really not a good idea to use the car GPS, or at least you should go on the field to collect that information. Another point is that you really often have errors in geographic coordinates. So what you should do, so for example, a very common one is inversion between the longitude and the latitude. You can have typos. You can also have errors when you transform the coordinates, etc. So you should really check that kind of information because it's often with errors. First, you can prevent the errors to appear. So before the data collection, for example, you can only allow plausible value for your project. So for example, again, in Belgium, the latitude is always comprised between 2 specific values and the longitude between 2 others. That's possible in Belgium because they are quite different. If possible, for example, in Lime survey, it's possible to ask people just to zoom on a map and click on the exact position. So that's better, of course, than just ask people to encode the data. But if you are using a spreadsheet, that's not possible. And then afterwards, after the data collection, you still need to check for the geographic coordinates. The first step is to make a map and check if some points are not completely outside your range. Another possibility is, for example, to compare it to the zip code. So this is an example here. What we do is we have the geographic coordinates provided by the people, and we have the zip code, and we compute the distance between the coordinate here and the center of the zip code area. We have the distance in kilometers here, and this allows us to spot high value. So for example, 71 kilometers is really too high. This spot was in France and not in Belgium, so the zip code here is not correct, etc. So we can eliminate that data. There are also sometimes a privacy and confidentiality issue when you have the exact coordinate, for example, of an apiary, but there is an easy way to deal with that, is to anonymize the coordinates by adding some random noise. And my recommendation then would be to keep the confidential data in a separate folder. So for example, with the personal beekeeper information and the exact coordinate, and in the general clean data folder to have only the anonymized coordinate with random noise added. Okay, then the last point, and maybe the most complicated one, is the question about what is each value about. So basically you have a table, and in each table a value is defined by its position in a column and in a row. So first you have to know what is in each column, and this is typically the metadata. You have to describe, you have to have the name of the column, so the table header, a description of the content of the column, the measurement unit, maybe the code or abbreviation used in that column. So that will allow you to understand what is in that column. But you also need information on the rows, and typically these are identification code, for example, for each sample, but also for each sampling unit of your project. The aim is to identify to which sample a measurement is related to, but also to cross information between tables. So this is an example. So the question is here, what is this number about? If you know that it's in this column, if you go in the metadata, you will quickly understand that this means that we observe between 14 and 60% of the needle. It's a kind of coniferous trees, so of the needle of the current year attacked by an invasive insect called Contarina. That's in the metadata, so that's on the column. And you also need information on the line, and here you can know, based on this information, that this value corresponds to the third shoot observed on a second tree randomly selected in a site called ACH01 in the year 2021. You can see here that the tree ID will be different in the different years. This is because each year we select at random a different tree. So the same tree is not measured every year. So it's normal that this ID will be different between the years and between the trees. On the contrary, the site ID will not be different between the years because we go back to the same site and we redo the observation on the same site. So this is to know what is the data about, but you can also use these IDs to cross information between the tables. So for example, here you have information about the pesticide content of a bee bread sample collected in the spring. So this is the sample ID of this sample. And in another data table, you can find exactly the same sample. And this is the pollen composition, the floral composition of the pollen. So you might want to use this information to cross the information between the table. If you don't know how to do that, I really encourage you to learn how to do that, either with a dedicated software, but it's also possible in spreadsheets. It's not really recommended, but if you are only using a spreadsheet, it's possible to do that, the crossing of that kind of information in spreadsheet. I think I will skip that part. You can go back to the slide, and there is a lot of explanation. So if you want to have all the information, you can go back afterwards. But the time is running, so I will not spend too much time on that. Yes, I think I will skip that one also. It's a bit complicated, but I will skip it too. Common problems with these codes are encoding errors and inconsistencies. So an example of inconsistency, here you have a site identification code, which is S01. And all these identification codes, in fact, are corresponding to the same site, but they have not been encoded in a proper way. So you can see here, for example, that we use what we call a trailing zero. We often do that so that the size of the code remains the same, and it's easier for sorting, it's easier for extracting information. So it's a common practice. The problem with that is that a human will see that as site number 1, and that somebody will encode it as S1 and not S01. But of course, the computer will not see that as the same. Another example here is with a lowercase s. So for some software, it will consider that they are the same, but other software will consider that they are different because of the lowercase here. This is a more tricky one. The second one here, it's not a 0, it's an uppercase O, it's the letter O. So again, the computer will consider that they are two different. And this one is maybe even more tricky. Basically, it's S01, but after that you have a blank space, a white space here. So that's extremely difficult to detect on a spreadsheet. So that's a problem, and you should really avoid that kind of inconsistency. And there are solutions for that, and they are the same as for the encoding error. So I will go back afterwards. So this was not an error. The encoder had the right code in mind. It's just that it was inconsistent. But you can also have errors, so the people can not select the right ID. So this is very risky, because if you don't have the right ID, the data will be not allocated to the right sample, and this might be very difficult to detect in some circumstances. So this is a difficult case, and typically the most important part here is sensibilization and training of the staff. Insist that this is really tricky and really important, and sometimes it's possible to do some random check, but it's not always possible. You have to keep in mind that errors will always happen, so I think it's really important to keep a psychologically safe working environment, so that people are not afraid to report, okay, I make a mistake here, what should we do about that? One of the solutions is to have as much as possible the clear labeling, minimize the mental load of the operator. So for example, prepare the label in advance, prepaste them on the containers, clearly identify the test items. So for example, the trap here has two clear labels. Predefine another possibility is to predefine a list of ID in the encoding table with a drop-down list, so that the people don't have to encode it, but just select it in a drop-down list. Another possibility is semi-automated recording with QR code. And of course, at the end, you can always check if there are errors, because you will have a reference list that will be with the correct ID, and check if the IDs that have been encoded by the operator match the IDs that you have in your reference list. So this is an example with a drop-down menu. So the idea here is simply that people have to click on the drop-down menu and simply select the right sample ID. So this will avoid typos problem, but you can still select the wrong ID. But what we have done in this case is that once you have selected the sample ID here, the rest of the table will be automatically completed with the corresponding information for this code. So you can see that it's in site situated in this locality. It's that type of traps. The date are between this date and this date. So this will help the operator to check if this is the right sampling ID. You can also see here that we have a red cell. This is because the number of days between the starting date and the end date is quite high. It's exceptionally high. It should be around 15. So this is again a warning to the operator to say, okay, maybe this is an encoding error. You should check that elsewhere in the data set. This is another example using a QR code. So you have an insect and a label, and the idea here is just that when you scan the QR code, it will just copy. It will copy the unique ID of this specimen, and you can then scan a lot of labels, and it will paste them in a table. So, for example, here what we did is grouping all the species of all the individual from the same species, scanning all the labels, and then you have that in a column in a spreadsheet, and you just have to add the species name. So, in that case, you reduce the risk of error because the operator don't have to choose the ID, or it does not have to encode it manually. Okay, so that was a huge part about what kind of information you should collect. And then the final one is about, now that you have your data, how should you organize the collected data for easier handling and data analysis afterwards? I made a list of a lot of rules and principles. I have 2 slides of it, and then afterwards it's a lot of example of all these cases. So the general idea is that you should have tidy dataset, and tidy dataset basically is the principle embedded in any true relational database system. So again, this problem will not be frequent if you use a real database system. It will be much more frequent if you use a spreadsheet. So again, it's mainly related to spreadsheet. So the basic principle is that in each column you should have only one variable, and a given variable should not be spread over several columns. And on each row of your table, you should have only one observation or one sample. And in each cell, you should have only one record. And finally, you should have one table per type of data, no more and no less. So you should not have the same kind of data spread over several tables, but you should not also put too much data in the same table if the structure is not the same, if it's not about the same thing. There are a lot of consequences from these 4 rules. For example, because you can have only one variable per column, you also should have only one type of data. For example, you should not mix in the same column text and numbers. You should also avoid to merge cell in a spreadsheet, because then you will not have one value per row and per column. You will have a group of value for several lines or several columns. So you should always avoid merged cell. You should never encode the data as color, as text formatting, or in cell comments. I will show you an example after that. And you should never add summary rows in the middle of the table. That's also very frequent. People put, for example, the average or the total of the columns. This should never be done because it's not the data. It's already computation on the data. It should be done in a separated file and not in the raw data. There is a question of long format and wide format, but I will explain that with an example. It will be easier. And then you should use unique IDs to identify the observation and to make to cross the information between the table. And we just spoke extensively about that in the part 2. And there are two very important rules that are not directly related to that. The first one is about missing data. You should clearly identify them, typically with 2 letters called NA for non-available, and make a clear difference from 0. So missing data is not 0. And a typical problem is empty cells. Empty cells is a bit ambiguous. You don't know if it's a 0. You don't know if it's missing data. So it's better to be explicit about that. And another point is that in order to have clean data, you should enforce strict and consistent variable coding. So we have seen that for the date, for example, people will change the format of the date. It's a problem. So you should use drop-down list and data validation rules to enforce people to use always the same structure, the same way to encode the data. So that's the general principle. I know that it's a lot, but we will see a few examples afterwards. Remember also the data integrity rules that we discussed before, so backups and never touch the raw data. And then there is also guidelines for good collaboration. I will not go in detail here, but if you want more on that, I highly recommend you this paper about that. But briefly, you should be open data ready. So for collaboration, other people should be able to read your data. So you should avoid proprietary data format and use only open source format. And either you should publish your data on public repositories like Zenodo, Feature, and we have this BeeHub repository for pollinators data. And then there are other recommendations to help other people to collaborate and use your data. Here you have a huge table from one of these papers, and it's a very good summary of everything I just said with a few examples and also what you should do, what you should not do, and why you should not do that. So again, I'll let you that for afterwards if you want to go back in the presentation. You always have the references below here if you want to go back to the full paper afterwards. So again, this idea of tidy data set, you should have only one variable per column, one observation per row, and one value per cell. So to give you a more practical example, this is typically what we call a wide untidy data set. It is untidy because you can see that here in the columns, this is not really the name of the variable. In fact, this is data. M is for male, so it's the sex, and the number is in fact the age. It's between 0 and 14 years, between 15 years and 24 years, etc. Typically, humans prefer this kind of wide format for several reasons, but this is not really handy to do the data analysis. So generally, you should prefer a long format. So you can see that it's the same data, but reformatted with a column for the sex, a column for the age, and then a column with the cases. And here also you can see that the cases, which are here, are in fact spread in different columns. But in fact, it's the same variable. It's the same information that is spread in different columns. So remember, you should have only one variable per column, and each variable should be ideally in only one column. One of the reasons that humans often prefer this kind of wide table, it's probably because it's easy to visualize at the first glance, but also sometimes it's for data entry and encoding reason. Sometimes it's easier for humans to encode data in this format. So I think that sometimes, normally you should always prefer a long, tidy format like that. But if you expect that it will increase the risk of errors of people encoding, maybe you should still stick with the wide format and expect some data manipulation afterwards, after the data encoding, in order to have it in a tidy format like that. An important point also is that even in spreadsheets, if you have data in this format, so in long format, it's very easy to transform that in a wide format like that. You can use pivot tables, for example, in Excel to pass from that format to this one. But once you have data in this format, it's much more difficult to pass to the long format. The only way often is just to do a lot of copy paste, and we know that this could cause errors. On the other hand, if you want to go from that wide format to this one in R, for example, or in Python, it's quite easy. Today, we have packages to do exactly that. This is another very typical example of wide untidy data. You can see here that you have 2 lines for the variable names. In fact, the problem here is that week 4, week 6, week 8 is in fact again data. It should not be in the name of the column. And you can see that the day, the weight, and the glucose are spread into different columns. Again, they should be in the same column. So here you have a tidy version of this data set. I will skip this one. So when you have that, it's still relatively easy, for example, in R to come from that format to a good format. So it's not much of a problem. It's much more complicated when you have this kind of table. So this is typically a table that has been formatted for humans. This should not be raw data. This should be for a report, for example, for a PDF, but not in the raw data. You have a lot of blank, you have a lot of text. It's really not cool for the data scientist if you provide data in this format. So this should be avoided, or you can provide both. You can provide raw data in a clean format and organize the data as you want for your report or something like that. Just to show you that, because afterward I will take artificial example because it's easier for discussion, but just to show you that this kind of problem really happen in real data set. These are 2 real data sets. Here it's data about winter mortality so each line is a different apiary and each column is a different colony. And you can see that you have colors here. And there are 2 problems. The problem is that data is encoded as colors, and the other problem is that missing data is not clearly encoded. The key to understand here is that the orange cells correspond to winter mortality. So this colony died during the winter. The white cell correspond to colonies that didn't die during the winter. But the gray cells correspond to missing data. It's in this apiary, there were no colony 5, 6, 7, and 8. The problem is that when you export this data to another software, the color information will be lost. And so it will be impossible to make the distinction between white empty cells and gray empty cells. And this is impossible to correct in R, for example. The only way is to re-encode all the data and complete all the cells. So this really should be avoided. This is another example. It's the same data set. Basically, it was really a very bad data set. There are plenty of errors in this case. So you can see, for example, that you have 3 columns for the pesticide, but in fact, it's not 3 different variables. It's just this line corresponds to the same sample, and I don't know really why they spread it to 3 columns. You can see that the pesticide name is in the same cell as the quantity of the pesticide. So again, you should split that in different columns. You can see that, for example, the name of the pesticide is not always the same. So 2-fluvalinate with 2A is the same as 2-fluvalinate and with 1A. This is English, this is Dutch. So this is another problem. You can see here that you have color and striped text. Again, if you export the data, you will lose that information. And in fact, we don't know really what we should do with that. Should we drop that information or not? So this kind of...
Sorry, Jill, to interrupt. We have 10 minutes to close.
Okay, I'm almost done. So what I wanted to do is use an artificial example to show you what you should do in that case. So this is an artificial example with messy data, and that's a tentative to clean the data up. So for example, here you can see that you have inconsistency in the ID of the site. We already discussed that before. So the solution here is to have a drop-down menu and to select a predefined range of values for the sample ID. Another problem that we already discussed is that the date format is not consistent. And you can see here that, in fact, we have a range of that is between the 1st and the 5th of May 2021. So in that case, you should have two different columns, and again, use some data formatting rules to enforce the user to use the right date format. Another problem is that in this column, you have a mixture of numbers, text. So for example, this symbol is text, the ASCII mark is text, and here you have a remark inside the column. So you have a mixture of number and text, and this will cause problems. So to solve that, you have to split all the information. So we have the sign to say, okay, in fact, here we had at least 15 insects, for example. It's not an exact evaluation. Here, it's probably an approximate evaluation. So what you should do then is have a column with the sign, a column with the number, and in the number column, you only have numbers with the only exception of NA for missing data. And then you can also have a column with the remarks, and you put everything you want in this remark column. You can also have a column with the data quality estimation. So 1 is for good exact data, 2 is for approximate data, and 3 is for data that you should not use, for example. Another problem is that you can see that data has been encoded as color. So you have a gray line here as a remark not in the cell, but as a cell comment in Excel. So it's a pop-up window. And also, for example, here as striped text. So this should be really explicitly encoded in the data. You should put that in the remark. So approximate evaluation should go in the remark. If this means that this is missing data, it should be clearly encoded as it's here, etc. Here you have another problem with ambiguous empty cells, so or symbols. Basically here, this would mean, for example, that the white empty cell is 0. You should then put a 0, and the gray empty cell is a missing data. Then you should put an explicit NA to make the distinction between the two. Another problem here is that people have merged the cells here. Probably because it was the same value for the 4 lines. But if you do that, and you export the data, what will happen is that the 6 will go on the first line here, and then the next 3 cells will be empty cells. So what you should do then is simply repeat the 4 values. This is the last one, I think, and this is the most tricky one. Here you see that you have some uncertainty on the date. You know that it was in March 2020, but you don't know the exact date, the exact day. This is tricky. This is honestly tricky. It will depend on the data set. One solution that we tested here is to provide a range of values. So it was between the 1st of March and the 31st of March. This is okay for some kind of data, but for example, if you want to compute the number of days during the trap, during which the trap was active, and then correct the number of capture based on that, this will be a problem, and this will not be an acceptable solution. Another solution is to simply drop the date information. So to put missing data, so NA here in the cell, but then you also drop the real information about the year and the month. And then finally, maybe another solution is to have 3 separated columns for the day, for the month, and for the year, and to have missing data only for the day. The problem then is that it will be difficult to make computation on the date, like computing, for example, the difference of the number of days between the two dates. That's it. I'm sorry I've been a little bit long. Personally, I have plenty of time if you have questions. So it's as you want.